Well, hello. Today we're going to talk about integrators and differentiators. This is the second part of chapter 13. And this is one of those operations that the op-amp circuit can do. We've already looked at summing and comparing two signals or more. Now we're going to look at how an op-amp circuit can perform calculus, integration and differentiation. Most of you probably, or all of you, have taken some bit of calculus in your coursework, and I've always thought that it'd be better if we, at least for us electronics people, we learned the integrator and differentiator op-amp circuits before we took the math, because when you take the math, you're most often being taught by a math instructor who's never really probably practically applied it in electronics. And I think it's really fascinating to me anyway to see that, okay, now I understand what integration and differentiation is all about, because I can see it actually operate in a circuit. And you have a multi-sim lab, that lab 13A Part 3, I believe, that you are going to build these things, and you'll see them actually operate, at least in simulation. Okay, so the integrator, basically, if you remember, it kind of measures what an integration is, measuring the area under a curve. So if you have a square wave or a sine wave or something like that, anything above zero, the integrator, as time goes along, is going to accumulate up that amount of area as time moves on. And that's exactly what this integrator does. Integrator has, as shown here, a capacitor in the feedback path, and then the input resistor. So normally an inverting op-amp would have a resistor in the feedback path and a resistor on the input. That feedback resistor is replaced by a capacitor. Now, the key to understanding how this works is remembering that this inverting terminal is what? Virtual ground. So we have virtual ground here on the inverting input. We have a voltage on the input side of this resistor. So a voltage across a resistor to ground, that's a constant current, right? That's a constant current. So that current is it's the IR drop, so it's V over R. That's the current, is the input resistance divided into the voltage. Now, where does that current go? It doesn't go into the op-amp, right? Because we're pretending this op-amp is ideal and there's no input current. So it goes through the capacitor. And when that happens, it charges the capacitor. Charges it at a constant rate because it's a constant current. And as a result, the voltage across that capacitor climbs at a constant rate. So you get a ramp, okay? So again, we have this capacitor in the feedback path that's getting charged at a constant rate, and it ends up basically being the running sum of that voltage. So if this voltage is on, if there's a voltage on your DC voltage, this capacitor is just going to keep ramping up and up, and basically measuring that voltage over time. And the more time that that voltage is on there, the bigger the voltage across that capacitor becomes. Now, if that voltage goes away, what happens? The ramp starts to come back down again. Okay, we're going to see that, I think, in some of these in the next slide. So for a practical integrator, a real one, okay, if you look back at this ideal one, what if there is a little bit of current going in here, or maybe an imbalance in these input bias currents? Well, that could be a problem, and that would result, even if you have 0 volts on VN, this capacitor is still going to charge because there's a small voltage here, right? So we don't want that to happen. So normally what we do two things. First of all, you choose an op-amp, and there's, again, hundreds of thousands of op amps, and you choose one that has a specification that has a very low or small input bias currents, or make sure that they're absolutely equal. And you can do that. You can go on DigiKey and choose an op amp that has those characteristics. The other thing we do is we add a small, well, actually it's a really large resistor, a couple hundred K or a megohm, right across that capacitor, and that tends to help things out a little bit too. It drains off that small voltage, okay? So we add a relatively large feedback resistor, like a 200K or higher, maybe a megohm. I've used a megohm. Now the other thing let's see, let's go to the next slide. Yeah, okay, so here's a equation. You're going to want to put this on your equation sheet, okay? And this is delta V out, that's right here, over time equals minus Vn over Rc. So this is the Rc time constant, so 10K, 0.1 microfarad here. So as long as Vn is something, okay, the R1C, when you multiply those together, it's a time constant. It's in seconds. So we have voltage over seconds equals voltage over seconds. Now it's a minus sign, obviously, because it's an inverting topology. So you get a negative ramp coming in if you have a positive voltage here. If you have a negative voltage here, you get a positive ramp. And we'll see that, I think, here. Here's the output wave. Here's the input wave. So we got 2 volts, square wave coming out, minus 2 volts. Then at 1.5 milliseconds, it goes up to positive 2 volts again. So it's a kind of like a square wave, not quite a square wave. Looks like it's got a duty cycle here. And so we look at the equation here. Delta V out over delta T is minus Vn divided by R1 or RIC. So 2 volts divided by 10K times 0.1 microfarad is 2 volts per millisecond. So when you sketch the output, you get a 2 volts per millisecond ramp. Okay, so it doesn't matter. What's going on here is that we get, okay, so going from 0.5 milliseconds to 1.5 milliseconds, we climb 2 volts, minus 1 volt to plus 1 volt. All right, in 1 millisecond, it's from 0.5 to 1.5 milliseconds. So that's what that shows. And notice that this is measuring the area under the curve. So as we go along here, okay, we're accumulating more area in time, okay, until we get to this point. So where it shifts back the other direction, okay. But as you move along here, this output is measuring this area. Look, it's going higher and higher and higher. Well, in absolute magnitude, of course, it's inverted, but we get minus 1 volt here because that's how long it was. That's how much area it measured under the curve. So that's integration. Okay. The other thing that's important to understand about integrators, okay, is that we use integrators, okay, as low-pass filters. What does that mean, low-pass filters? Well, we're going to talk about filters in a few weeks here in the beginning of March, but a low-pass filter is a filter that passes low frequencies. So when you think about this, this is a feed. If you replace this capacitor, remember it used to be just a feedback resistor. That's what this is. This capacitor is what? This is a very high impedance at low frequencies. Matter of fact, it's an open circuit, a really high resistance at low frequencies, meaning the gain of this op-amp circuit is really high. So very high resistance divided by a very low resistance would be a very high gain circuit, right? All right, so that means a low frequency is going to get through this thing. Let's move it up to high frequencies. Okay, a high frequency shorts out this capacitor, right? Capacitors are short to high frequencies. So this is going to be a low a low impedance divided by your input resistor. So as soon as you start lowering that feedback resistor in impedance, in ohms, you're going to get a lower gain circuit. So it attenuates high frequencies. So sometimes we say, well, I'm going to integrate out that frequency. What that means is you're going to put some sort of op-amp circuit in there that's an integrator to filter out those high frequencies. Now the fact is that you'll often see in circuit diagrams, practical circuit diagrams, a small capacitor across a feedback resistor. And the primary purpose of the op-amp would be just an inverting op-amp. Okay, it might even be, this might even be like a 10K resistor and 10K resistor here. So a gain of -1, right? 10 divided by 10 times minus, the minus is going to be a gain of -1. I might, or some other designer might put like a 30 picofarad capacitor across that resistor. And you look at it and you think, well, it looks just like this circuit. It's an integrator. Well, not really. All right, that small 30 picofarad capacitor is performing integration, but really it's there just as a filter. It just filters out a little noise. All right, a little high frequency noise, in fact. A circuit that's, and you can kind of tell when you look, of course, obviously have to understand what the circuit is for, but if the designer is primarily intending it to be just an inverting op-amp, then, and he has a capacitor in there, or she has a capacitor in it, you're going to see that that capacitor is going to be very small, maybe 30, maybe 100 picofarad max, very small. Now, if you see a circuit that has 0.1 microfarad or 1 microfarad across a large feedback resistor, that's different. That is clearly an integrator, all right? They're not trying necessarily to filter out high frequency noise. Oh, it'll filter out high frequency noise, all right, but its primary purpose is to do integration, right? Not inversion or amplification or anything like that. Okay, I hope that's clear. Let's go on. Let's see. Okay, so here's a multi-sim circuit, multi-sim simulation here, and you'll see it's they put a square wave in here, plus or minus 2 volt maybe. Square wave, yeah, or maybe it's 4 volts, 1 volt per division. Yeah, and you'll see it ramps up and down every millisecond here. Yeah, this is 500 microseconds, so this is a millisecond, so it does go up 2 volts per millisecond. You can build this, I think you will build this in your Lab 13 Part 3. Yeah, this is what we showed on the previous slide. All right, differentiator. Now remember, calculus differentiation was the opposite of integration. Okay, and it's true here too. It's math applied to electronics, or electronics applied to math, however you want to look at it. But check it out. What has happened here? We've reversed the positions of the capacitor and the resistor. The resistor now exists in the feedback path, and the capacitor is on the input. Now, first thing I want to point out, all right, is that the differentiator is what? Is it high pass or low pass? Remember, the integrator was what? Low pass. You know this is high pass because there's a capacitor in series with the input. And any high frequency is going to short out that capacitor. A low frequency, like put a DC battery, a 1.5 volt battery, it's not going to get through. You can't pass DC through a capacitor. So therefore, low frequencies are attenuated and high frequencies are amplified. And you can do that with any circuit. When we get a little further on in the course, so we're going to look at filters, and we'll be doing that exercise. We'll take all the capacitors in the circuit and short them out, simulating a high frequency input. And we'll see what the circuit looks like. It completely falls apart and simplifies itself. And then on the other side, we'll put a DC battery on the input, a 1.5 volt D cell, and see what happens. All the capacitors go away. So in high frequencies, all the capacitors short out. They become wires. They go away, become wires. And in low frequencies, they just disappear altogether and they disconnect. So in this case, for low frequency, it's going to disconnect. So in this case, the output is proportional to the rate of change on the input. So if you have a ramp that's coming in from your integrator, for example, it's going to charge this capacitor in a linear fashion, produce a voltage across it, a constant voltage, that will be reflected on the output. So let's take a look. Okay. In the next slide we'll look at some curves, but the practical differentiator is very sensitive, as I said, to high frequency. So oftentimes we put a little series resistor here, okay, to attenuate those high frequencies. Also, this helps balance out the bias currents. And you could do this on the integrator too. This resistor on the non-inverting input, okay? So here's the equation. You're going to want to put this on your equation sheet. V out equals minus VC over T times RF, the feedback resistor, times C. So notice that as time, if you study the equation, VC is the voltage across the capacitor, which is increasing. Time is increasing. The RF is constant and the C is constant. Okay, actually voltage across the capacitor is constant. I misspoke. It's not increasing, it's constant. T is increasing. Don't we all know that? Time keeps going up, right? Hopefully. So as this increases, as T increases, what happens to this expression? It decreases. And we have a negative here also. So let's take a look at some curves here. Okay, so here's our input where we have this curve, okay, and this ends up being this is the input voltage, okay. Minus 1 volt is the voltage across the capacitor, which is our input voltage, ramping. And so we have minus 1 volt over 0.5 milliseconds. That's its rate. That's the rate. So it's minus 1 volt per millisecond. All right, so it's a constant ramp, is what I really should be saying. It's a constant ramp. It's not really constant voltage, but it's a constant ramp. 1 volt for 0.5 millisecond. So that's what this VC over T is. Times 10K times 0.1 microfarad equals 2 volts. So you get a constant 2 volts here. And then when it switches, goes the other direction, you get a minus 2 volts. So it's measuring the slope of this line, right? So this is 2 volts per microsecond. 2 volts per microsecond. So it's an indication of the slope of the line. And maybe you remember that a differentiation actually measures the slope of a line from your calculus, right?